Okay. Welcome everybody to the virtual time series seminar. It's my great pleasure to introduce our speaker today, Raffaella Giacomini from UCL. She's joined by our guest panelist, Tatevik Sekhposyan from Texas A&M. And the topic is perceived shocks and impulse responses. So Raffaella, the floor is yours.
Thank you so much for the invitation, and thanks, Tatevik, for agreeing to be a panelist. So I think some of you have actually already seen it, but we now finally have a paper which will circulate soon. So this is a joint work with Jason Liu at the IMF and Katia Smetanina at Chicago Boots, and it's about essentially beliefs about shocks and impulse responses. So the idea is quite simple of the paper. So in a nutshell, essentially, this is starting from the premise that we have a lot of expectations data available. They've been widely studied in economics, but typically they're studied to answer a specific question, which is trying to understand expectation formation process, maybe testing rationality and other theories of expectation formation. So we're not going to do that. So we are taking the same data set, and we kind of highlight that there is this dimension in a lot of these data sets that has been underutilized. And by providing a method to utilize this new dimension, we can answer new questions, which are not about expectation formation in terms of testing theories, although they could be used for that purpose. But essentially, they are a way to extract from these expectation data two key quantities that we care about in macroeconomics, which are shocks and the impulse responses, so the dynamic effects of the shocks, obviously through the lenses of the agents that are forming the expectations in the data that we have. And I want to say I'm happy to take questions during, so stop me anytime. So the essential idea is the following. So the type of data, which is actually widely available, is a panel. But the panel is not necessarily in terms of the individuals, although this could be applied to the individual level data as well. But so the panel is that we have revisions, which we will construct, of one variable over time and across a term structure of forecast horizons, so different points in the future. So that's what we need. So we need in the data forecasters to provide a number of forecasts for a set of future events at any point in time. And they do this month to month. And so once we have this type of panel structure, then the idea is very simple, which is to fit a time-varying factor model, and then to recover the latent, so they're both latent, the factors, which will be interpreted as the shocks, and then the loadings are the impulse responses associated to each shock. And this is at every point in time. Okay, so the time-varying aspects really allows us to have time-varying shocks and time-varying impulse responses at every point in time. So a very important point is that we want to have a robust method, so we don't want to impose too much structure. And we do this by being non-parametric, essentially. So first of all, we're using principal components and also non-parametric estimation of the time-varying loadings. But also we will see that this is robust in a broader sense, in that it only uses the expectations data. So we don't have to bring in other data, which means we don't have to make assumptions about the information set that the agents use, the model that they use, or also the type of whether they're rational or not. So we're just simply seeing what's in the data, and we're extracting whatever we see from the data in terms of their behavior. And then the method will be particularly designed to reflect a constraint of this data set, which is very plausible and realistic, which is that the horizon dimension is going to be very short, typically. So we're going to have to adjust existing methods to account for the fact that we're working with very small samples. So basically, why is this interesting and why is it new? So I think that the impulse response aspect is perhaps the more novel and interesting, because this is, to our knowledge, essentially a new measure, a new empirical measure about beliefs on the persistence, essentially, of shocks and also the shape of the impulse response. So we're going to back out a direct empirical measure of what these agents, possibly even individual agents, think of in terms of the dynamic effects of shocks. So why is this interesting? So first of all, this is directly interesting to central banks because we care about anchoring of the long-run inflation expectations. And there's a big literature about this. So we're going to have a way to extract essentially these unobserved components, which allow us to answer some policy relevant questions. On the other hand, we can use this to document perhaps new stylized empirical facts about shapes of impulse responses, persistence of shocks or beliefs about these objects. And this is relevant to these theories such as the Blanchard, Lhuillier, Lorenzoni, where beliefs about the persistence itself drive aggregate fluctuations. And more in general, this is going beyond this a very, very rigid dichotomy between permanent and transitory shocks that we're very used to seeing in economics and in macro, particularly for modeling inflation, as in the Stock and Watson famous paper. And this is allowing for the possibility that the shocks are not necessarily either transitory or permanent, but they're persistent. And we're going to learn about that persistence. So the part about the perceived shocks is less novel because this is very related to what we do already in the big literature on narrative measures of shocks, in the sense that we're already looking at revisions around certain events. So in a way, what we're contributing, I guess, to this literature is that we're telling how to leverage this dimension of the data, which is often present but underutilized, which is the horizon dimension, in a formal way. And we're going to see how we can extract from this horizon dimension a shock. And in a sense, this was already in the original Gurkenak, Sachs, and Swanson, where they apply principal components. So they extract one principal components for different measures of high frequency measures, narrative measures. So we're going to instead focus on one specific measure across horizons, and we have a formal way to extract the shock. So we also allow for parameter stability. So the shocks we extract are going to be very different. And also we're going to tackle the problems of this very small dimension. So we need to really do something that is not just principal components to make this rigorous. So now I'm going to just say that the biggest question on everyone's mind right now is, in what sense can these be called structural? And this is the same. So in a sense, we're not really saying anything new, although there's a potential for answering new questions. So in other words, we're just having the same problems that the literature has in, calling these extracted objects structural kind of involves other assumptions about, exogeneity and whether there's some other information. So in a sense, we're not able to provide anything new. We're just simply coming up with different measures of the shocks that are exploiting that horizon dimension. There is a sense, and I have some discussion about this in the paper, but there's not a general recommendation in which you might be able to actually expose, after you have extracted certain shocks, to call them maybe a supply or a demand shock based on differential, perhaps, effect on prices and quantities, but that's not generally available, but it's a possibility.
So Raffaella, can I just ask a clarifying question for a second? So usually, in this monetary policy literature, there's an FOMC announcement date. So that sort of pins down the structure, right? And then I can revise. And then, of course, there are some issues with that. But, let's say blue chip is monthly. So, revision will be monthly. So within a month, who knows what happens. So that's kind of what you have in mind, in that, you might still need some mapping to call.
Yes.
Okay.
Yes, exactly. So that's the frequency, definitely, if you can manipulate. So that's one way, right? So manipulating the frequency is what allows you perhaps to assume that there's only one specific shock that occurred during that interval. So that's kind of the high frequency argument. Another one could be imposing maybe some restrictions on the impulse responses that, as I was saying, help you recover, perhaps because now we're backing out not only the shocks, but their impact. So we might be able to say, okay, so these people, they think that this is a shock that has an impulse response that has a certain, it moves the prices in a certain direction and quantities in a different direction over time. So we can call this a supply and this a demand. But that's not generally true. And of course, what we're extracting is everything the agents react to in between subsequent revisions. Yeah. So that's not necessarily new. So what's new is really just looking at, because at the moment that they're doing a revision, they're they're reacting to whatever they didn't anticipate the previous period. And we're also seeing what they think this dynamic effect of whatever that information is going to be in the future. Okay, so the data is very simple. So we have a panel of these forecast revisions. So H will be the forecast horizon. That's the cross-sectional dimension. And T will be the time, the frequency at which in our data, the agents produce forecasts. So as Tatevik was saying, in the blue chip, it would be monthly. If you have maybe some analyst data, it would be more frequently. If you're looking just specifically around certain announcements, it would be very high frequency. Okay, so the revisions, you need to construct them from the data. You kind of need to back out, because often at every point in time, you're going to have a set of future horizons, H. And what you want to consider at every point in time, so at time T, so month, so say today, September, we have a forecast for the current quarter and then the 4 quarters of the next year. And so the revision is that if we go to October now, we're still going to see the forecast for the current quarter and the quarters of next year. And we're going to look at how the forecast from the same object, okay, so that's important. We're keeping the event fixed, and we see how we change from month to month the forecast of the same quarter or the future 4 quarters of next year. Okay, so we're looking at, these would be our raw data. So we need to kind of construct that, pay some attention to these issues of mixed frequency, for example, because if you're having monthly revisions, sometimes you fall within the quarter and sometimes you fall without, but that's easy to keep track. Okay, so now we're going to take these revisions, which can be mixed frequencies. They can be at horizons, they can be very different. It can be 1, 4, 8 months, or 5-year inflation and 1 month ahead inflation. You can mix also different objects. And we're going to fit a time varying factor model to this forecast revision term structure. Okay, so we're going to have some time varying loadings potentially, and some smaller number of factors, FT, and some idiosyncratic errors, EHT. Okay, so this structure will allow us to recover the FT are the perceived underlying smaller number of shocks that are driving revisions across all horizons. And then lambda HT will be whatever the agents think is the impulse response, which is the effect of each shock at each of the 1 horizons in our term structure. We're going to talk about the assumptions a bit more formally later. Okay, so of course, these are not separately identified, so we need to impose normalizations. And now what's neat here is that we may be, depending on the application, we may be more interested in shocks or impulse responses. So if you want to carve out, back out the impulse responses, you can normalize the factors, because then now you can interpret the impulse responses as the effect of a unit standard deviation shock. Now, if you want to recover the shocks, you can normalize the loadings. So you can interpret the scale of the shocks. Or you can also, if you want to make intertemporal comparisons across of the impulse responses, you can also normalize the shocks to have a unit impact. So the time variation is quite important here. Of course, we can only do this if we have quite a long T. So if we don't have a long T, then we're not going to be able to do time varying impulse responses, but we can apply the method still, because this is a finite sample method. So this works even in very finite samples. For example, individual forecasters may not have a long time series, whereas consensus forecasts have a quite long T. So in that case, the long T can be really leveraged to really understand time variation in perceived impulse responses. So we want to be flexible in modeling or capturing time variation that has potentially any type of shape. Of course, so we're going to impose some continuity assumptions, some smoothness, and we apply the usual sort of, smoothness, non-parametric estimation via kernel methods. And this was done by Motta and Su and Wang, because we're going to apply principal components because we want to be non-parametric. They consider principal components with time varying loadings. However, importantly, these are all large T and large H results. So they really need a large cross-section. Like, we don't have a large cross-section. So in our data, we have the biggest we could find is 7. Okay, so definitely we're not in a large H. situation. So we know that small h poses some real problems for principal components analysis. So we know that the problem is essentially the noise is the heteroscedasticity, which of course we don't want to assume homoscedasticity. So as long as there's heteroscedastic noise, we know that PCA is invalid in finite samples. And so this is, there's some very nice literature in statistics in the matrix completion literature that has acknowledged this problem and proposed a solution, which we take essentially and adapt. So also the literature in statistics does not consider time variation. So essentially what we're doing, we're taking this matrix completion approach and we're adapting it to time varying parameters. Okay. So this is called heteroscedastic PCA. So this is a very nice paper in the Annals of Statistics by Zhang and co-authors. Essentially, it's an algorithm that works in any finite sample. So this can be applied to even very small problems. So small, expectations where you really don't have that much information. And then we're going to extend it to time varying parameters. Okay, so the factor structure may seem arbitrary. So some people may think that, okay, does it make sense to postulate the factor structure for revisions? And here we show that actually this is quite natural. So this is a very sort of arises naturally within existing theories of expectation formation, starting from your rational expectation that no one likes anymore, but also including some information rigidities such as the popular noisy information model. And you can see this very easily in this context of the Plackborg-Moller vector moving average. So assume that your agents are rational, okay? So they use some correctly specified model, which we know in a very large class of cases can be expressed as a vector moving average, okay? So this is not that restrictive. So suppose that they have a multivariate model, but then here we're only considering one equation from that vector moving average. Okay, so this YT is a scalar, is one of the equations in the vector moving average. However, there are multiple shocks, epsilon t. Okay, so these epsilon t are all of the structural shocks that the agent is reacting to. And then the theta L is the log polynomial, which in this case represents directly the structural impulse response. So if you're looking at what this model implies for forecast revisions of one variable in the system between two consecutive time periods, by keeping the horizon fixed, you see that the revision of the same h horizon variable between t-1 and t is exactly giving us a factor structure without idiosyncratic noise. So this is, there's no additional noise. And here the factor R, the vector, so the vector of structural shocks, potentially we're able to recover the whole vector of structural shocks from looking at the horizons for only one variable. Okay, so we don't need to really start assuming that the forecasters are using this model to forecast different variables. So if they just forecast inflation, by looking at how they forecast inflation across horizons, we could in principle back out multiple structural shocks to the extent, of course, that we can do that given the very small sample problem.
Can I ask a clarifying question for a second? So this notion that H is small, usually T is small in these applications, right? I mean, so, and you have this kind of representation. I mean, so this is parametric. I can estimate this thing. So why do non-parametric in that sense? Because,
it's the same problem, right? So parametric, you're going to have to deal with heteroscedasticity as well. So in a sense, of course, there might be some trade-offs because, of course, if you start assuming normality for the idiosyncratic shocks, you might be able to do the Kalman filter. And there's some literature that suggests that there might be better the principal components, but then it's the usual trade-off, parametric versus robustness. So we think that because we want to use non-parametric estimation of loadings, we want to see sort of what is what can we say under the weakest set of assumptions? And in general, I'm really into robustness lately, which I know is always difficult to, so I'm making my life more difficult by starting from the most robust, the weakest assumption. Can we still say something? Now, it might be that in some cases, this is not giving you enough information, then you might want to see by, maybe you can get more by putting some distribution assumption, which you then have to defend. But yeah, so you could apply the Kalman filter here. So it's also interesting, I think, just to see how the, these information rigidities also imply a factor structure, which is perhaps less obvious. So if, okay, here I just wanted to say, I already said this, so forget about it. So the information rigidity is this, in this very simplest case of the Koibiona-Grondlichenko example, where you have one variable now, say inflation, you're forecasting a variable, and say the true DGP is an AR1. So Gaussian, very nice structure. And then the agents don't observe the true variable, but they observe a noisy signal with like a Gaussian noise. And so then they use the Kalman filter to extract the signal from the noise. So essentially their forecast for the H horizon at time t is just given by this object where they use the Kalman filter. And what's nice in this model is that the Kalman gain is the degree of information rigidity, but whatever. It's not so important here. What's important is that when you look at the revision in this model, forecasters are still keep extracting the noise, but they revise a forecast. It turns out that the revisions themselves has the nice factor structure again, where the factor now is essentially a filtered shock. So it's a surprise from the Kalman filter updating equation, which kind of we think makes sense. Is you're updating that's your surprise. Whereas the loadings are the actual true, in this sense, impulse responses, or structural in the sense that if the agents are using correct specified model, they're recovering the true impulse responses, even though there's noise. Okay. All right, so back to the method and getting more into the econometrics, unless there are other questions about the setup. So we're gonna have this model in vector notation, okay? So we have all of our revisions for all of our H horizons, which are few. Then we have our loadings, and now we're gonna add idiosyncratic errors. So assumptions are borrowed from this matrix completion literature, okay? So I highlighted the most significant assumption here, which is the third one in blue. So the first are uncontroversial. So here we're dealing with the revisions, so it's plausible that the factors have mean 0. Now here, the second one is just highlighting that the variance is fully, so it's a fully heteroscedastic model here. So the variance can differ across H's and T as well. What's really important here, and this is something we cannot relax, we could relax a little bit, but not fundamentally, is that really, in order to make this method work, we need to have independent errors across H. Okay, so this is really something that we lose by going to small h, because in large H, we know we can allow for some weak dependence. But as in small h, we really need to leverage independence of the idiosyncratic errors across horizons. The fourth one is something that's not essential. In fact, we showed that in a Monte Carlo that we can have correlated shocks, although we think in principle shocks shouldn't be correlated, but in practice they might be. And in fact, they are in our application. So, but that really changes absolutely nothing into the performance of the method. Second assumption is normalization. As I said, you have to choose which one to normalize depending on what you care about. Now, first assumption, so the fundamental assumption, first of all, you need to ask yourself, how plausible is this in any given application? So as you notice that in the theoretical, looking at these theories of expectation formation, there is no noise implied by these nice models, but in practice, there may be noise for several reasons. For example, we'll be considering consensus forecasts, looking at the average in the blue chip. And so the average, it means that every month, there are different agents, different forecasters that participate. And also not all forecasters give a forecast for all horizons. So there's a compositional effect that introduces some noise. There's also some rounding of forecasts that affects different horizons. And you also, as we do, maybe mixing different types of forecasts, or also we're merging two different surveys. So we argue, but of course this has to be defended, that arguably this type of is more like a classical measurement error that really is independent across horizons and time. But if it isn't, then really all breaks down. Now, just to give you a flavor of what's going on here, what is the problem of this small h and heteroscedasticity for PCA is that, you know, we can allow when T and N are large, everything is not a problem. However, so when there's a small n, so essentially the problem is the following. So we'll be looking at these covariance matrix, local covariance matrix of the data, the sigma t. And under some normalization, we can really decompose it into the two covariances of the common component, which is now under the normalization on the factors really gives us the loadings, and then the variance of the idiosyncratic errors. Now, normally when you have a large, sorry, it's not n here, it's h. I forgot to change that. So when the cross-sectional dimension is large, the factor dominates, so we're able to recover by looking at the eigenvalues and eigenvectors of sigma t. We essentially can attribute that to the factors, sorry, the loadings, the lambdas. So we can sort of ignore the idiosyncratic part. However, when the h is very small, we might have that, well, and there's a heteroscedasticity, so there's a particularly maybe a very large covariance, variance of one of the idiosyncratic errors that dominates. And so essentially what happens is that the eigenvalues and eigenvectors of the two objects are very different from each other. Okay, so they're no longer, you know, in large samples, we can say that we're looking at the eigenvectors of sigma t, but these are essentially the columns of lambda t. That's no longer true under heteroscedasticity. So now, what's the neat solution that the Zhang and Kotos propose, which is essentially a way to take care of this? So the solution essentially is under, that's where you see now the assumption really kicks in, the assumption of independence of the idiosyncratic errors, is that the problem really is only the diagonal, essentially. So if we can ignore the off-diagonal elements, it's really just the diagonal elements that are messing things up. So essentially what we do is we kind of eliminate that diagonal, and we kind of recursively substitute the diagonal with the diagonal of the best low rank approximation in an iterative fashion until we kind of don't see the eigenvalues changing that much anymore. Okay, so it's a very simple idea. So, you know, people still do this sometimes. They put the diagonal to 0. The novelty here in this Zhang co-author is that they do this iteratively. And they show that this works really well. So it takes care of the bias of PCA in very small samples, and we confirm in our simulation that this works really well. So essentially the idea is the same. So what we're doing here is that instead of applying this idea to the global covariance matrix of the data, we apply it to a local, non-parametrically estimated local variance covariance matrix of the data through a kernel regression, a kernel estimation of that covariance matrix. That's all. And so we do this at every point in time. So that was kind of the fundamental assumption that you see why that independence really makes this work. The other assumptions are pretty harmless. So one, of course, you need the smoothness of the time variant parameters. This is very standard. There's a bit of a twist here because since we are not separately identifying loadings and factors, we kind of need to ensure continuity. We need to add some extra step in the algorithm to make sure that you know, the continuity actually is what helps us recover, pin down essentially the sign of the loadings from time to time. So that's a bit of tweaking that is necessary here. And then there's this very big high-level assumption, which is called incoherence assumption. In this matrix completion literature, this has been used by Imbens and co-authors. There's a very nice paper in microeconometrics by Agarwal and Singh. They have a discussion about this. And so essentially what they also discuss in this paper is that this incoherence assumption that they make in this literature is similar to assuming strong factors. Okay, so essentially what you want to avoid is that all of the loadings are close to zero or the very large number of loadings are zero. Practical implication of this is that if you apply this methodology to data where you don't have that much updating, or if you choose a very small bandwidth and you're not seeing that much movement, then you're gonna run into a weak factor situation and it's not gonna work very well. Okay, so the algorithm is very simple, just kind of summarizing what I already said. So it's a two-step procedure. So in the first, we start by estimating a local covariance matrix of our revision, non-parametrically, using some kernel, and you can choose the bandwidth by cross-validation. Then you take this local covariance matrix, you set the diagonal to 0, you do a singular value decomposition of this matrix with 0 diagonal, then you find your low rank approximation, low rank in the sense that you assume a certain number of factors, and then you're finding, the approximation that given those number of factors. And then you take that diagonal elements, you put them back into the original matrix, and you keep doing this iteratively until the eigenvalues don't change that much anymore. So then in the second step, you're going to have to impose this continuity of the loading, so you have to renormalize things. So then you get nice continuous loadings. Then you can do a very nice residual-based bootstrap, because here we're assuming IID errors. So it's a standard case of a residual-based bootstrap. Of course, these are going to be point-wise confidence intervals. So the punchline is that essentially, how does this work in practice? Because we have in our data, and in this type of data, you're not going to be able to have more than, say, a handful of like 7 or 10 horizons at best. So of course, it's all well and good that we can in principle recover multiple factors, multiple shocks, but can we really, given that we have a very small H? And so we do a bunch of simulations, it's really important. And so we find that you could, in principle, in our empirical application, recover a second factor. So even though we have only 7 points, we could potentially recover more than one factor. However, now once you start introducing time-varying loadings, both the second factor and the loadings of the second factor are less precisely estimated than the loadings and the factor for the first principal component. Okay, so, but you can recover the time variation. And of course, because we're going to have non-parametric estimation, if you're looking at the very beginning and very end of sample, things start to break down a bit, even though you use these one-sided kernels. Okay, so you have to take with a grain of salt what I was saying in the application, which is about the recent inflation episode.
So Raffaella, just a quick question. When you say recover a second factor, so in a simulation, there is a second factor with some properties, and then, so what exactly you mean by recover a second factor?
Yeah, no, that's a good question. So it's just that because we have this test, right? So we apply this Onatsky test, and we see whether the test will recover the second factor, even though it's like a time-varying version of the Onatsky test in a very small sample, which we don't know in principle whether Onatsky works in a finite sample. But we find that with some decent power, we will be able to recover the second factor. Yeah. Okay, so this is sort of like optimistic message from the simulations. So let's see how it works in practice, okay? How can we apply it to see anchoring of inflation expectations? Okay, so we're gonna apply this to historical, so we're applying to a very long time series of inflation expectations, because we're mostly interested in seeing, here we're mostly focused on the impulse responses, because this seems like a new idea, new question. It's like, are they changing over time? Do we learn something about anchoring that is new? So to do this, we have a problem. So we started with the blue chip Panellist forecasts. Now the blue chip are very nice because they're monthly, as Tatevik was saying. So we can obtain, the problem with the blue chip is that they do the following. So every month they give the forecast for the current year and the next year. So it means that in December, they're only giving 4 quarters of the next year. Okay, whereas at January, there's 8. So we could potentially, have as many as 8 horizons, but if we want the month-to-month, something that is available every month, we only have 4, plus the current quarter. So we have 5 horizons, which are short and medium, so they extend to 4 quarters ahead. But we want to look at anchoring, so we want some long horizon expectations. Now, the blue chip, unfortunately, only asks infrequently about long horizon expectation. They don't give long horizon expectations every month. However, the Cleveland Fed does something smart, which is sort of as a way to interpolate these infrequent blue chip expectations using high frequency data. And so they issued this monthly forecast, which importantly is aligned with the issuing of the blue chip. So that's super important that we align the information sets if we merge different expectations data. In this case, we think is defensible. Now, we're not going to talk about the first finding, which is, we apply, is there more than one shock? We could potentially recover the second shock. Are these people reacting to multiple shocks? And we find that essentially our test overwhelmingly shows evidence for only one shock. We really don't recover any evidence of a second shock. And then when we try to understand what the shock is, we try to correlate it with a bunch of different objects, and we find that it's highly correlated with the inflation surprises, in particular with the surprises from the Stock and Watson stochastic volatility model. Okay, so it's like 87% correlation. So it seems like these agents are really kind of, looking at the residuals from a simple model of inflation alone. They're not necessarily looking at many other data. Now, the second stylized fact that we find is more about impulse responses, which is this interesting when we allow for full non-parametric estimation of the type of time variation, we really seem to observe this secular decrease in what agents think is the persistence of shocks, of the one shock. Okay, so it's really, this seems to have decreased over time. And so essentially this is linked to a notion of de-anchoring. So what we can say is that even though in recent times we have seen, like a lot of dynamics in inflation, agents continue believing that this was not due to the anchoring, but it was just the presence of large shocks. And we're able to do this formally because we're able to disentangle these two unobserved components when we observe large changes in long run inflation expectations. What are they due to? So we see that here. Okay, so first of all, this is the outcome, right, from our method. So we're applying this to our term structure of forecast revisions from this blue chip merged with the Cleveland Fed. And then at every point in time, we have these time varying loadings. So each one of these lines is loadings for the different horizons. Okay, so essentially the way you read an impulse response is by looking like this, and you see that, the way they decay is giving you the impulse response at any point in time to that particular shock. And so the distance between the different loadings is telling you how rapidly the agents think the shock is decaying. So you see like this, but if you look at all of these slices, vertical slices, you really see that there's quite a lot of variation in the shape also of the impulse responses over time. And the way you see the persistence is essentially how quickly sort of the long horizon loadings go to zero, how close to zero they are. Of course, I didn't report confidence intervals, but we can put confidence intervals here, so we can do this more formally. So we can do this by selecting 3 different data points just to see these vertical slices. So here I'm selecting 3 particular times. So the blue one is in the 80s, which was the the Volcker disinflation period, where inflation was going down really rapidly. And then we have the red line, which is during the financial crisis of 2009. And then we have the more recent high inflation episodes, the green line in June 2022. Okay, so you do see then here we're imposing a unit impact normalization because it nicely allows us to compare these different impulse responses over time, whereas the previous picture also had a different, standard deviation of the shocks over time. So here you do see this secular decrease that I was talking about. So even though in the 80s, you saw a quite slow decay of these shocks. So this shock was a disinflationary shock. However, there was a persistent, a belief that the effect of the shock would be quite long lasting. And so if we want to think of the anchoring as this being significantly different from zero, we do see that the anchoring here. Whereas in the recent time period, the green and the red, you see just generally speaking, the two are very similar, even though we are in two very different situations. One is the financial crisis, and now is the high inflation period, but there's essentially a similar belief about the impact of these inflation shocks. And now if we want to answer this question, sort of like a policy relevant question, which is, okay, so there's been a lot of discussion, at the central banks, you see, you're monitoring very closely what happens to long run inflation expectations, and you start worrying if they move a lot. Then the fundamental question you want to ask is that, okay, there are two reasons why they're moving. It could be because agents are really observing a big shock, so they were surprised by inflation that was going up, or because they think that the effect of even a small shock is going to persist. And so you want to be able to really tell the two apart because they have very different policy implications for a central bank. And so we can do that because we have exactly a way to extract these two latent objects. And we can do this by comparing, for example, what happened in 2022 versus the Volcker disinflation. And so now the blue is still the Volcker disinflation, the red is now the recent inflation episode. So we have the two objects, right? So on the left, we have our impulse responses, and then on the right, we actually have the whole series of extracted shock to inflation. And what you see is that I'm smoothing it a little bit on the right-hand side. Okay, so, but what you see is these two things that really jump out, subject to the caveat that this is our N sample. Okay, so there might be some bias because when we move towards the edges of the sample, but you do see that during the Volcker disinflation, you see, which is this vertical line. So the shock was a negative shock, was disinflation. So the agents were surprised, but in terms of the magnitude of the shock, this was quite, the magnitude was historically normal. Okay, it wasn't a particularly large shock according to historical standards. However, even though the shock was small, the agents believed that the shock would persist. Okay, the effect will persist. In recent times, we have this historically unprecedentedly large shock. So these agents were really surprised in June 22 by a very large shock. For a few periods, they kept being surprised by this large shock. However, they thought that the shock, essentially the effect would disappear within 4 quarters. It wouldn't really last beyond that horizon. Okay, so you do now, maybe it's a positive message, or maybe not, maybe the agents were wrong. So see, we don't really know, right? So but there is, to the extent that we really want to see what, maybe these were not markets, but maybe we care about their beliefs. We don't care about whether they're right or wrong. If they believe that the shocks are going to persist, they're going to act on it in a different way than if they believe essentially they're just a surprise, but it's going to die out. Okay, so I'm just going to conclude so we can all go home. So this was a way to see how we could exploit this existing horizon dimension that is available in several expectations data set that is now not really formally exploited. And we can do so by adopting this factor model approach. Now we do have to contend with the fact that this is a small h, okay, small cross-section. So things may really break down quite quickly, but luckily we have these very nice methods that are very kind of robust. They don't rely on very strong assumptions. The important assumption is this idiosyncratic error that has to be independent. And And the nice thing is by being a finite sample, you can apply not just a consensus forecast, but also individual forecast. And I'm working with my co-authors in trying to extract some information from individual expectations about heterogeneity of shocks and impulse responses. That's all. Thank you very much for your attention.
Raffaella, can I ask you a quick question, actually? So this is really cool. But can you do exactly the same on Green Book forecasts and then like have some notion whether, you know, there was like a misperception or misalignment in the perceptions of the Fed versus the private, you know, whatever, private sector in terms of like whether things were transitory or permanent, like, you know, or the persistence of things? I mean, that would be kind of cool.
That's a good idea. Yeah, exactly. Because then you're really you're not imposing any assumption. That's what I like about it. You're really only using information in the raw expectations.
Yeah, exactly.
So it's like whatever these agents believed, and you can try perhaps, so another thing we're doing now is looking at the forecast for inflation and growth. Yeah. So you can really see, you know, are they reacting to the same shocks? Yeah. Are their beliefs compatible with economic theory? So you can start asking a lot of cool questions.
Yeah. Yeah, that was my second question. Like, can you just add like output, you know, expectations in there and then try to say something about?
Yeah, we're doing that.
The Phillips curve or something.
An array that is doing that right now. Like, do they make any sense? Or I mean, you can learn indirectly. You know, I said that it's not about expectation formation, but it is, right? In this sense, you can really ask questions about, are these people rational in that sense? Do they apply economic theory?
Wonderful. So thank you so much, Raffaella, for a wonderful talk.
Of course, my pleasure.
To our guest speaker, to our guest panelist as well. I'm going to stop the recording now, and then we can move to the informal discussion.